Jason. Can you get a little water in there for me? I forgot enough time. Thank you. We ready to go? Should we get started, or is that a yes? Are we good? Okay, great. I guess I was waiting for somebody to kind of tell me to go, and I guess it was me. Anyway, my name is Bruce Momjian. Super excited to be here. It's been a great conference so far. How many of you attended the unconference the past 2 days? Yeah, I mean, was that positive? How many liked the unconference? Yeah, I was just, wow. It seems like we've got a great sort of pattern of sort of exchange and working on stuff and kind of, brain power discussion, and that's something that's sort of missing from the lecture format. I have a tendency to have a lot more interaction in my formats, but again, it's a personal preference. But again, I just found it really valuable. So I'm looking forward to that. Again, named Bruce Momjian. I live in Philadelphia. I am one of the Postgres core team members. Been working with it since 1996. And I work for Enterprise DB. I've been with them for 9 years. And obviously, we've been around for a long time, sort of adding enterprise tooling and support and capabilities to Postgres and working with enterprise customers. So I'm very happy. It's worked really well. I'm loving the conference. How many of you were just over at the compilation tutorial in 1140? Yeah. So it's the funny thing is I'm over there. Thank you very much. And I'm pulling up the slide, and he pulls up a slide, and I'm like, hey, that looks kind of like one of my slides for this presentation. So those of you who are over there, you're actually going to see some stuff that actually is related to what he was talking about. So it's kind of a bonus for you. I did not expect that. So what is this presentation about? It is about basically how Postgres uses shared memory, how Postgres processes communicate, how Postgres sessions communicate. I've been working, obviously, with this for 19 years now, so I'm intimately aware of how it works, and I will also say that how it works and how it does what it does is one of the things that fascinated me about Postgres. So if you're the type of person who is interested in sort of understanding what happens inside and how Postgres does what it does, I think this will be a really interesting session for you. You're not going to see any SQL in this session. Again, the focus is mostly on how Postgres does what it does, some of the sort of overarching architectural decisions that Postgres has, and we're going to dive into some of the internals and sort of see. And again, a great presentation for PGCon, where a lot of people have a tendency to be more server development, internals people. And I think you'll find this very interesting. Again, I like to get questions as I speak, so feel free to ask a question and we can talk about it. That often makes the class more interesting, or the training more interesting. I'm actually in my native element here because I was a high school teacher for 5 years, and I am an adjunct professor at Drexel University. So sort of like Blackboard / lecture hall is very natural, a little scary natural, but again, it's wonderful you came today. So what are we going to talk about? We're going to talk about 6 major things. First, we're going to talk about how Postgres stores its data, which is a little on the simplistic side for people who are used to much more complex systems. And I'll explain why it's designed that way. That's how we do it, why we do it that way. Then we're going to talk about shared memory. For those of you who aren't familiar with it, I will explain what that does. Process creation, also something we're going to talk about and kind of give you an overarching thing there. A lot of times when I'm explaining the architecture of Postgres in training classes, I have to go to these slides because these slides really, I think, give you sort of a foundation of what is happening inside Postgres. And when you understand that foundation, you're much more able to sort of see what is that process doing, how is it doing it, what does it mean when there's lock intention, what does it mean when I create a new session, all these things that are kind of hidden for ordinary users you're going to have a world into. And then we're going to talk about how we actually look at rows, how rows are looked up. That was actually the point that was talked about in the optimizer session before this. We're going to talk a little about locking and other structures and then finish it off. So any questions before I start? Am I loud enough for everybody? Everyone in the back can hear me? Oh, was he? Okay, great. Okay. No questions? Okay, so kind of the first surprise, I would say, to people who come to Postgres from other databases is that Postgres uses the file system solely to store its data. So unlike systems that maybe use raw devices or special hardware or some sort of mixture of those, for Postgres, everything is stored in the file system. In fact, everything is stored in the file system under a directory that typically is called data, which is very unimaginative, but that's usually where it is. There's an environment variable called pgdata that usually points at this. And this directory has everything. It's got the configuration files, it's got the system tables, it's got the tracking of which transactions committed, it's got the write-ahead log in most cases, it's got all your data files and all your indexes. Okay? So everything is in there to the extent that if you shut Postgres down and you just back up the data directory, you have backed up your database. Okay? So everything is in there. Makes it very easy to administer, makes it very easy to debug. You do LSOF, and you can see all your open file descriptors. There's nothing hidden. Okay? If you're running on a VM, again, there's no sort of backdoor kernel, get me to this special region of the drive. It's all in that directory. Okay? If you install multiple versions of Postgres, multiple clusters of Postgres on the same machine, you're going to have multiple data directories. So typically, if you create 3 clusters and put them on different port numbers in a server, you're going to have 3 data directories in 3 different parts of the system. They may be on separate file systems. They may be on different areas, but they're somewhere in that file system. That's basically the way Postgres does anything. And that data directory is created initially by the initdb command, which probably most of you have heard of. It's an internal command or a command that you would use to initialize Postgres. If you're using an installer, a lot of times the installers will run initdb for you. But if you've had to run it yourself, that's what it does. It's creating that raw data directory for you to use. Okay? So again, very simplistic, doesn't use anything fancy, very good for administration, very good for virtual machines. When VMs came around and we were like, what do we need to do special? Not much, really nothing. Now, you're not restricted to the data directory. You can store stuff in other table spaces. There's a symbolic link that goes out to other table spaces. So you're not locked into one directory for all your data. But again, this is going to be your main source of data. This is going to be where your config files live in most cases. And then you can spread out from here, but this is where everything starts. OK, any questions so far about that? OK. So you kind of learned the first thing is that the file system is kind of the go-to place for Postgres. I know a lot of other databases use raw file systems and sort of fancy storage. Basically, that was designed in the old days when file systems were very primitive. Think like System 5 Release 3, fragmented, had all sorts of sort of problems with throughput. But if you look at modern file systems today versus a raw device, there's not a whole lot of advantage. Maybe there's 2% if you're lucky by going raw versus a file system, but it's not worth the headache. It's not worth the administration. It's not worth the rigidity that you have of using a raw device. So Postgres has never implemented it. I doubt we're going to. We've been very happy with the development that has occurred within file system design to make that easier. Yes, sir?
It also works well with a simple file system, doesn't it?
Yeah, it works. You can put it.
You're tight on memory.
Yeah, I mean, and people run Postgres on like PS3s and other crazy devices and whatever. So we just don't feel that a sort of a raw device where effectively Postgres has to write the file system, is really a good use of our time. And we do think that it would make it quite difficult. And if you look at what vendors are recommending now, they originally recommended raw file systems because of their speed. But now, in most cases, they're saying, unless you need that extra 2%, just don't go there, because there's a lot of headache in that, and having worked with Informix and done raw file systems and had to compute how big I had to make my extents and stuff, I am glad to see that go. And in fact, when you start to look at how we do replication and backups and so forth, a lot of that is tied to that whole file system. So there's a synergy in how Postgres does things that may come across in this talk, but in that because we choose a very basic solution, we can put things together using crash recovery for replication, using crash recovery for point-in-time recovery, adding logical replication on top of crash recovery. There's a whole bunch of sort of elegance that we can add in the sort of Unix sense because we've got basic building blocks, and those are built on the file system. Makes any sense? Any questions? So what is in that data directory? Probably the most important directory that we're going to talk about for this is actually the base directory, which is a really weird name for, I always think of acids and bases when I see that. But why would you call it a directory base? Well, because it's a data base, right? So when you put the two data directory and the base directory, it makes database. Remember, this was originally designed by university students, and I thought they probably thought that was a cute idea. So it's called base. Okay. You also have other directories, which I'm just going to talk about real briefly. The PGX log is where we keep the transaction log. The PGC log is where we keep the status of committed transactions. This PG table space here is where we keep the symbolic links to the table spaces. So I said that you can use table spaces in Postgres and other file systems, and that's where they would exist. Okay. We also have a global directory for global tables like the usernames and so forth. But the base directories we're going to focus on here, we're going to drill down into it. Inside the base directory, you have a number of subdirectories. Makes sense? Let's use the file system for that. Effectively, you are going to have a subdirectory for every database. So in this environment, we have 1, 2, 3, 4, 5 directories under the base directory. So therefore, we have 5 databases defined in this particular cluster. Let me say one more thing. This presentation is at that URL right there. So you can download it right now. It's PDF. There's probably 30 PDFs there. So I always forget to mention that. Sorry about that. So here we've got 4 directories. Number 1 is actually template 1, which is sort of a special database. The other ones are test, develop, marketing, whatever. We're going to look at the production database in this particular case. Inside the production database, which happens to be 16385, we have a number of files. Okay? And they're numbered. They're numbered. So in this case, 24692 is customer. 27214 is order, and so forth. Normally, you're going to have many more files in this directory than just this, but I'm just showing you a couple of them. There will be some system tables in there. But effectively, inside of here is every table and every index. Those are the 2 things that get stored here, plus some things like the free space map and the system tables and the visibility map. Also, we're going to have, be in this directory, they're going to have special extensions, _VM or _FSM, to track everything that's going on in that particular database. Yes, sir?
Is there a way to easily map between the pretty name and the number?
Yes, that was going to be my next sentence. Having worked in Informix and having sort of to look at a directory and restore one, and you couldn't figure out what it was that you were trying to restore, there is actually in the system catalogs a particular field in the PG class table called rel file node. And rel file node will map to that particular example. I do have an administration slide deck on my website that shows you how to use rel file node to look things up. There's also a tool called OID to name you can run from the command line, which will do a query and look up that name that goes with the number, so you can create shell scripts that show me the biggest 5 tables from the command line, right? And then you sort them, and then for each of the 5, you look up the name based on the number. We would love to have used the names, and originally in the 90s, first for a year or two, we used the names. But then the problem was people are always renaming indexes and renaming tables, and it's very hard to do that atomically because obviously you would have to do you'd have to lock anybody for referencing because they're referencing the file name. So now we allow the name to be changed because effectively it's all referenced by the rel file node, which does not change. If you rename a table, the rel file node stays the same. So we had to do it that way. And then there's other problems with long table names and UTF-8 table names, and we didn't want to go there. So I would love to have used just the names, but we can't. Other questions? OK. So let's take a look at one of these files. So here is actually, let's see here. This is 24692, which happens to be our customer table. And basically, the tables are all going to be made up of 8K blocks. You can change that by recompiling Postgres, but by default, everything is going to be a list or an appendage of multiple 8K blocks. If the blocks get over a gig, we will create another file, which is again made of 8K blocks. So we have what we call segments, and you can create on 1 gig at a time. We'll create multiple segments to make sure we don't overflow your file system limits. But effectively, we got these 8K pages, and everything is sort of stored that way. Inside the 8K page, it looks like this. Okay, so that's one of the 8K pages that particularly appear in the table. At the beginning is a table header. At the bottom is some special thing. At the beginning, you have what are called item pointers. And at the end, you have what are called rows or tuples. And the item pointers grow from the beginning to the middle. The tuples grow from the end to the middle. When the two meet, the table's full. And we create a new page. The item pointers are particularly important because we move these things around a lot as rows get added and deleted. But the item pointers are pointed to by the indexes. So the indexes actually have pointers to these. So that allows us to move rows around on the page without having to touch the index. And that's really one of the major reasons is it allows us to move things around while keeping the reference, the external reference to that row at a fixed offset within the page. Okay. And again, those are 8K. So let's go inside a tuple. So remember, we've gone from the data to the base to the directory that matches the database to a particular file to an 8K page. Now we're going to go inside a row. So this is sort of like we're going smaller and smaller and smaller. We've got our 8K page, our particular tuple here, or row. What does that look like? It actually looks like this. So this is the row. It actually has a header and then a bunch of values that append to that. The header has a whole bunch of tracking information related to when the transaction was committed. In fact, these are virtual. We don't have all of these fields in there. But we have the OID. We have the number of columns or add fields in the row, an offset for the nulls, which is back down here. And then after the header, you have a bunch of values. Okay? And this is where we start to kind of get specific on particular values. Effectively, because Postgres was designed as an object relational data store, meaning you can add data types to it and functions and index and so forth, every time you access a value in the row, a field in the row, you actually have to call a special input or output function to get the value in and out, because Postgres doesn't know what an integer is. It doesn't know what a text field is. It doesn't know what a CIDR or a JSON. The code that's looking at these rows doesn't know exactly what's stored in there. All it knows is that to get the value out, I have to call an output function. And to get the value in, I have to call an input function. So for example, this first value in the field is actually an integer. And it will call a function called int4in with a string. And that function will return a 4 bytes of memory. And the system will store those 4 bytes in memory because he says that's what the input function told me is the binary representation of that particular string. In the flip side, when you want to get a value out, we're going to assume that the fourth field here is a text field, and we're going to call what's called text out. And text out is going to look at the offset or the bytes at the particular entry of offset within that row, and it's going to return an actual string. In this case, it's Martin, happens to be stored there. But again, you can see that we have not hard-coded information about data types. All that information is kind of stored in external functions. We do have a couple short-circuit things, I think for int4 and a couple others, where we kind of say, you know, I know it's int4, so I'm going to do something special here and not call a function. But in almost every other case, this is why Postgres is easy to extend, and also why those system tables are so important, and why you can add data types to Postgres, because you can very easily just define the input function, define the output function, and all of a sudden Postgres can deal with that data type, a data type it did not know about before. Yes, sir?
I have a question about CTIDs. So they change whenever you end up writing a row to a different location in the table, right?
You're talking about the item pointers.
The CTIDs?
CTID is effectively the TIDs. So that's actually the item pointers that sit at the front, and they point to specific rows within the block.
So one use I've seen for those is to disambiguate between duplicate rows when you somehow end up with rows that all the column values are duplicates. Is that legit? Is there a better way to do that?
So the question was, can you use CTIDs to find out rows that are identical within a table that are duplicates? Is that right?
Right. So in other words, you do some query where you say, select the CTID plus star, everything in the table.
Yeah.
If you want to dedupe it, you just do the min, effectively, the CTID for identical rows.
Okay.
And you just delete that one.
Yeah, so the question is, can you use CTIDs to effectively do stuff within a table? We would probably discourage that, because the CTID is really tied to the storage of the row, and it doesn't really track things like a row getting updated while you're running the query, because the CTID is now going to be somewhere else. I don't remember if we actually follow the CTID pointer if you access it. So the CTID, we really would not normally have people looking at those. We would probably recommend some kind of primary key, although again, if you're saying that the rows are identical, then maybe, that's a good question. Robert, I saw you twitching your hand. I was hoping you had a good answer for this gentleman.
Yeah, so I think the case that you're speaking about, if all the visible rows, all the visible columns in given rows look the same, then you kind of have to revert to something that is not quite as visible. So that's where you go look at the C2. But if you're going to do that, I mean, there's a good point around what you really want to do is select those rows for update and get like a block on them so that no one's going to actually update those in the middle of what you were doing. Which could even be like the auto vacuum process in the background could suddenly magically just change some C2s around and then we delete them. So if you select those for update, get a lock on them in a transaction, then look at the individual storage on disk of that C2, and then you can delete that, and that's pretty safe for getting rid of duplicates. So you got to be careful with it, but it's otherwise not too bad, because it is pointing at different storage locations. So there are distinct physical rows on the machine someplace, right? Even if they look the same when you query them, looking at the SQL values.
Well, yeah, thank you. That was great. Appreciate that. Other questions? Okay. So what I've kind of shown you is the idea of drilling down and looking at an entry, the idea of sort of doing. Now, let's take a look at some of the details. This is actually the layout for the header in C. Okay? So you're actually looking at the info mask, the bits for nulls. These are the sort of, what is it here? This is the xmin, xmax, cmin, cmax sort of union of values. So effectively, all this stuff is not magic. It's actually defined in C. And we have a whole bunch of macros to access them and make, sort of access. And when we add a row, we're having to look and create structures that match this particular layout. So any questions? Again, I've kind of drilled down all the way. I want to go into the next topic, okay? Yes, sir.
You talked about the item IDs getting shuffled around at some point in time in event. What are some of the use cases? When does that happen?
So when would the rows get shuffled? The CTIDs can get shuffled around in an update situation particularly. What happens is when you do a query, you will get kind of a page lock as you're looking at the physical row, but then once you leave that, once you go to the next page, you won't typically maintain the lock on that. So the CTIDs are particularly volatile because an update would cause perhaps that CTID to be unvisible or invisible to you, and a new CTID for the same row that somebody would update would just be somewhere else. So if there's cleanup on the same page like vacuum would do, that's not going to change the CTID. Because the CTID is a pointer into that page. You can move things around on the page. The CTID is not going to change. It's really going to be something like an update or perhaps a vacuum that removes the row, and therefore the row now points. The CTID now points nowhere. That would be another case where Robert's idea of doing the select for update. So you do have because you're within the same query, you're not going to have a problem because the row's not going to disappear while you're looking at it. But when you run one query and then you go to the next one, unless you're in serializable mode or read commit or repeatable read mode, you're going to get a new snapshot. And that snapshot doesn't know anything, really is not maintaining any kind of state about what that row meant, and it could definitely change. Great. Let's get to the next thing that I wanted to cover, and that is how Postgres is effectively laid out. The shared, we talked about sort of how the data is stored, but let's look at more of the shared memory portion. So Postgres is process-based. This is often another surprising thing to people because they're used to having databases which are basically one huge process which has multiple threads running inside of it. Okay, so you have a big address space, you've got one executable, and you have multiple stacks effectively, which is effectively what a thread is. It's a stack within that, and your operating system is scheduling multiple threads within that particular executable, and perhaps multiple threads at the same time within that executable. Okay, Postgres does not do that. We actually have a process-based model, and there's some major advantages to that. First, from an administrative standpoint, you're not looking at sort of one big blob that you have to sort of pick apart. I remember when Informix went from process to thread, monitoring what would happen in that system all of a sudden became very difficult. Practical advantage for developers is it's a lot easier to do development on a process-based model because threads are really hard and it has a shared data space, so everything you allocate all of a sudden has to have a lock around it. We've been very happy with sort of the process-based model. Fortunately, most operating systems are very good at creating processes. Process creation and thread creation on Linux is about the same overhead. So again, it's a really cheap way of us getting a very stable environment. You're much less likely for a random session to corrupt things in this process-based model than you would in a thread-based model, aside from being easier to program. The only places where threads are actually less overheaded processes significantly would be on Windows and on Solaris. I think those two have very heavy processes and very lightweight threads. So in those environments, ideally we would have done threads, but for almost every other environment, every other workload, we're good with this. If process creation is a problem for a high volume system, we often recommend some kind of connection pooler so the processes are reused on those particular environments. So, if you kind of look at the layout here, effectively what happens when Postgres starts, it starts something called the postmaster, which is your listener or your connection, your initial connection process, which originally talks to the person who wants to make a connection. Assuming that connection is considered to be valid, we will use an operating system command called fork, which will make a copy of the postmaster. So you can see how kind of elegant this is. You're not really creating a whole new binary. You're just duplicating the binary you already have and that it was already listening, and it inherits the file descriptor, the socket, okay? and then continues, and the postmaster then just goes on to do what it was doing before, and that is listen for new connections. So again, very elegant design. You basically do the fork. What happens in the fork is that your program text, your actual program is identical, because again, it's using the same pages. So you have two processes here. They both have the same pages. They both actually share the same stack and the same data segment, although the amount of sharing that goes on between the postmaster and a particular session is fairly small, which is indicated here by very skinny lines, sort of sharing between those two. Okay. So effectively, you're creating a new session here. It's starting to process the loop to understand SQL. It gets the query, it parses it, it optimizes it, executes it. That is a huge amount of work, obviously, that goes on in a single SQL query. Threading is really good if you have a lot of small tasks you want to do. Like, you have a GUI and you want the hourglass to keep spinning while you're updating some other part of the screen. That's a very lightweight case, but databases are pretty heavy. There's quite a bit going on here. So the idea of spending the time to create new processes is pretty logical. Okay. But the problem that the process model has is that these processes are private. Even though you forked a child, every time you change some data in your local data heap, no other process is going to see that. Okay? It's got a copy and write mechanism, effectively preventing anybody from seeing any changes. You get a copy of everything. As soon as you modify it, you get your own private copy. So how do you get the system to work and do all this very complicated orchestration and coordination and so forth if if your data segment can't be shared? The answer to that is shared memory. So this pink area down here is effectively all of the area that you want to share among your sessions. Okay? And that's basically how Postgres does it. In a typical thread model, you have some shared data in your data stack. You have some data that's private to that thread. Postgres, effectively, we just said everything we want to share, it's going to go in a shared memory segment. And it's going to be mapped into the same address or a similar address across all the processes. It's going to all be the same size. If I change a byte in one part of the shared memory, people see it right away. Anything you want to do private, you do in your own data segment. Okay? So you can see that it's a very clean design because effectively you've taken everything you want to share and you put it in a separate part. Okay? And that's kind of the magic of what allows Postgres to do. And we put a lot of stuff there. The shared memory area has probably 15 or 20 or 25 different structures, all of which is shared. And again, we've taken the time to sort of separate out everything we want to share, and we put it in this one place. So the biggest area that you're going to be using your shared memory for is the shared buffers. So this is going to be pretty much all of the I/O you do is going to happen in the shared buffers, because effectively if I read a page, somebody else wants to look at that page, we want to make sure we show them the same page, right? Like if I read some data and you read some data and we both modify it, we both write it out separately, one of them is going to overwrite the other, right? So you don't want to do that. So you have a shared buffer area, which is your common area for every time you're going to read some pages, every time you're going to modify some pages. You're going to do it not in your own local data space, but in that shared buffer space. We also have a way of tracking that with both buffer descriptors. There's a proc array I'll talk about, which actually has an array for every session that's running. We have a whole bunch of tracking stuff related to things like two-phase commit, multi-exact, synchronized scan. Again, a whole lot of stuff in there that every process is able to access. So let's put the two together. We've talked about the data directory and the 8K pages and everything. We've talked about shared memory as a way of allowing these processes to all communicate. Let's put it together. So effectively, the shared buffer area, which is the area I said where we do all of our I/O, all the reads go into the shared buffer area, all the modifications happen in the shared buffer area, all the writes from Postgres of all sessions happen in the shared buffer area and then get written down to the file system at some later point. Okay, that's like the big staging area. Effectively, it's broken up into 8K pages. Super surprise, right? We already said that the disk is broken up into 8K pages. So we've got effectively our shared memory area maybe is broken up into 8K pages. So if you have 8 megs of shared memory, you have 1,000 8K pages. Unlikely you have 8K only of shared buffers. If you have 8 gigs of shared buffers, let's suppose you have 2 gigs of shared buffers, right? Then you have 1,000, you have, let's see, it would be 1 million shared buffers would be, so you have like 250,000 shared buffers in 2 gigs of shared memory, which is a typical figure for a large server, okay? And effectively what you're doing in this area is if a database, if a particular session needs a page or a block from the file system, it will go to that file system at the specified path. It will seek out to the offset of where it wants to load that particular page. It'll say, give me 8K from that file, from that directory path. At this offset, give me 8K, and write it right into that shared buffer area. Okay? And then once that happens, I can then read it, I can modify it, I can write it, and other people can read it and modify it, and then effectively write it. I may not even write it. I probably will just read the page and then just move on. And some other process like the check pointer or the background writer will actually be the one that either throws it away because nobody wants to read it anymore and it hasn't been modified. But if it has been modified, then somebody's going to have to write that down, and that's usually either background writer or the check pointer. So I don't even have to worry about writing the changes I make, partially because this is a shared area. So I can like say, oh, I'm done with it, and I just leave it there, and I let the cleanup process come along in some other session that isn't waiting for a query, that isn't currently executing a query, and it wakes up every so often and says, oh, we got a lot of pages here. These haven't been modified. Let's throw them away. These haven't been modified. Let's write these down. And then we can throw them away because they haven't been accessed in a while. So all that cleanup is happening in other sessions. But my point is that whole 8K idea that is baked into the file system effectively is baked right up into the shared buffers. And we have a buffer descriptor area which is doing the tracking of who's reading these pages, who's perhaps writing them, and therefore we shouldn't be modifying them. This gets back to that whole thing with writes. So again, the 8K page actually looks like this. The tuple itself looks like that. And your reading and writing of those fields, again, has the same text in, int for, out, whatever, sort of a thing. And then they're all coming from that data directory. What's kind of interesting is that when you're reading a particular field in the shared buffer, which again is a copy of what's on disk, there's not a whole lot of sophistication there. Effectively, it's just a pointer. So if this is actually some C code that's in the back end, which is effectively walking through a row of a particular table. So we have a loop here, which is basically like, let's see here. So this is our loop. This is our for loop right here. Okay, and it happens to be called no cache get adder. We have a whole bunch of functions like this, so I'm just picking one. But effectively what it does is it says, okay, I'm going to walk. I have like sort of an infinite for loop here, and I'm going to look at the first field. And if the first field is a null, then I'm just going to skip over it because effectively it's not, we don't store nulls. So we just go advance and then move to the next number. If that particular field is not null, then if it's a variable length field, then we effectively hop over the length of that field because we have to get from that field to the next one. It's variable length, so we have to look at the length, and we just say, okay, it's 20 bytes. Let's move 20 bytes farther along. If it isn't a variable length field, we can actually look at the alignment and the value of that particular field, and just without reading the data, we can just know that's always 8 bytes. We just, okay. If it's the row we're looking for, if it's the field we're looking for, we break out of the loop. If not, we just kind of advance and align ourselves and move forward to the next field. And then once we've kind of gotten to the field we're interested in, we effectively just call a fetch for a particular byte, and we have an offset that we've been accumulating an offset here which keeps getting bigger and bigger. And we just say, give me the row, go to that offset, and that's what I'm going to do. So I'm kind of walking. If I have a row that of 10 fields, and I want the fifth one, I got to walk through 1, I got to walk through 2, I got to walk through 3, I got to walk through 4. When I get to 5, that's how I'm going to return it to the upper levels. Okay. This is even more complicated. Remember down here I said we have a FetchATT. Effectively, what this FetchATT does is it's going to say, okay, is this field I'm looking at an integer? So if it's an integer, then I'm just going to actually take the field and I'm going to take the memory location. I'm just going to map it as an int32 pointer, and I'm just going to return it to the person. If it's an int16, means like an int2, I'm going to return that as a user. If not, I'm going to actually kind of map it as a character pointer, and I'm going to return it to the user. And then if none of these are true, then I'm just going to return the pointer to that particular. So what I'm trying to do here is I'm trying to map that particular byte of data. So the interesting thing I think here is that a lot of people think that when Postgres stores its data, it's storing its data in some like magical format, like some format that Postgres designed from early on, and integers look this way, and strings look this way, and it's not really true. Like when you're actually storing an int4 or an int8 in Postgres, we're just taking whatever the CPU thinks of as an int4 and int8, we're just writing it to a memory offset. So there's no like translation of a lot of these native values. It's just that's exactly what the way that CPU wants to store an int8. So therefore, we're just going to take that pointer, and when I'm accessing that, I'm just saying, here's an int4 pointer, put the number 5 there, and it's just going to write at that offset in the shared buffers. It's going to write that particular value, and then eventually it's going to get stored to disk. And when it comes back, it's going to come back exactly the same way. And when the system needs to read that int4, it's going to read the int4 in the same way. Yes, sir? So what if you move a database from a big endian system to a little endian system? It will not work. In fact, one of the downsides, this is very fast and very simple, right? So it works really well, but the downside is that it will not work. It's tied to that CPU. If you go from 32 to 64-bit, it will not work. Not only the endian order is an issue, but going from a 32-bit OS to a 64-bit OS on the same physical CPU, all of a sudden things are slightly different in alignment, and therefore it also would not work. So you'll get an error. Try and start it. It'll know it doesn't work. But it's kind of an interesting approach. Some databases have sort of a neutral format that they use that allows that kind of migration. Postgres never had that, and again, I think for performance and simplicity reasons, we're probably going to stick with what we have.
So is there any, would you get a intelligible error out of that, or would it just be like
You'd get an error on startup. Yeah, they're one of the PG control. You would have a PG control error in your server logs that said, what would it say, Jim?
something like not L compatible or something like that?
Yeah.
When you see it, it's pretty obvious.
It's so obvious that no one ever asks me, like, what does this error mean? Because they must move CPU types a lot. But whatever the error is, people are like, okay, I got it. Because I don't ever remember seeing a question. I mean, maybe every 6 months or 9 months we'll get a question about moving it and it didn't work, but it's pretty clear, yeah. Yeah, so the PG control is pretty clear when it doesn't match something, yeah. One final thing I wanted to look at is how we do locking. So locking is kind of, again, very low level for Postgres. You sort of get that concept of simplicity here. This is an illustration of what we call a test and set instruction, where you actually have two processes, one over here and one over here, they're both trying to put a 1 into a particular byte in shared memory. It would have to be in shared memory, right, because it wouldn't make any sense anywhere else. So if you put a 1 in and you get a 0 out, then you have succeeded, you have the lock. If you put a 1 in and you get a 1 out, then you've actually, somebody already has gotten the lock. And this allows for concurrent locking in a very efficient manner. Effectively, test and set says put a value in and get out the value that used to be there. So when you get a 0 out, you know that there was no 1 there before. If you get a 1 out, you know there was a 1 there before, and therefore you did not get the lock. It is so low level that we have CPU assembly language specific instructions for every CPU type that we support to implement test and set. So this particular example is from Intel x86. I think this is a 32-bit example, but effectively you're doing the exchange byte, which happens to be the assembly language instruction for test and set on that particular CPU. But again, very low level, you're calling assembly language here to do locks. Sometimes you don't want, like what if your lock fails? What do? We have another type of lock called a Spinlock, which means that if I get success, I'm fine. If I don't get success, I'm going to sleep for a random increased amount of time and then go back and try again. So again, sort of building on the test and set, you have the Spinlock. This can be good. This cannot be good because, again, a lot of spinning is not going to be always good. At a certain point, you're going to need to sleep. And we have something called lightweight locks, which effectively allow you to sleep on a semaphore and get woken up when that lock becomes available. So you have sort of a hierarchy of locking that you can do. Depending on how long you think you're going to need the lock and how long you think you're going to have to wait for it, you have those options. Okay? As I mentioned before, we also have a proc array, which tracks all active sessions, again, also in shared memory, so that we can know what all the other sessions are doing and do coordination. And that's what the proc array looks like. Okay? So that's the last slide, kind of reminding us of what we're storing in shared buffers. Again, what we talked about is how do we store the data in the data directory? How are those AK pages made? How do we store a row or a tuple? How do we get data values in and out of that field? And then we started to talk about process creation and fork and shared memory and how that works. And then we started to talk about shared buffers, how the pages are copied into shared buffers, and then how we do some of the locking with the spin lock and the test and set lock. Okay? Yes, sir. I probably have 1 minute left. Yes, sir.
Just to take one example of something where coordination has to happen, how do the shared buffers get allocated to individual processes?
So how do the shared buffers get allocated to individual processes? The fact is they don't. The shared buffers themselves are just this amalgamation of bytes. Okay. So what happens is if a particular session wants to make a major change in a particular page, it will actually use a buffer descriptor. And the buffer descriptor, you'll put your tag on that buffer descriptor that said, I am in the process of making changes to that page. Anyone who comes along who wants to modify that page or even see it may be required to wait until you release the write lock on that particular page. The beauty of this is because a lot of this is happening in assembly and a lot of the test and set, you're going to hold that buffer pin, we call it, very briefly. And actually, I take that back. A buffer pin means that nobody else can modify it while I pinned it, but a buffer write lock would be don't get in there while I'm moving things around. And that would be where you would do it in that buffer descript area. Okay.
So each process can sort of find any page in the shared buffers that are available.
Any process can find any page and do whatever they want with it. Yeah. And there is some code there to prevent things like cache wipe from large scans and stuff like that. So we do try and sort of ameliorate the major disruptions from a session. But in general, by default, they have pretty much total control. Yes, sir.
I'm interested in writing some tool to observe shared memory outside from outside of Postgres for some debug purpose or troubleshooting purpose. So it would allows us to look at shared memory without touching Postgres. Is it possible or useful?
So could you write a tool that actually looks in shared memory without looking at Postgres? You can. I mean, there is a contrib. This is a great point. There is a contrib module called PG Buffer Cache, and it allows you to look inside a Postgres shared buffers and see what's there. You could very easily also write a process that just attaches to shared memory. The shared memory offset or the ID for the shared memory is in the postmaster.pid file as one of the lines. So you could actually just say, I want to attach to that shared memory, and then you could do pretty much whatever you want. The reason most people do it from PG Buffer Cache or a contrib module is there's a lot of infrastructure inside the backend that knows how that data is laid out. And normally they would create a plugin to do that, because then they can harness all of the infrastructure there. Okay? I believe I am out of time. I believe it also is lunchtime, I think. So thank you very much. I will be here if you have any questions.